Let's talk about rigid bodies. For translational motion, we have talked about the point particle model, and that model works pretty well in that scenario. We can imagine point particles translating, and all works well. However, once we encounter rotational motion, we run into an issue with the point particle model. What does it mean for a point particle to rotate or spin about itself? Can it? Does it? It's really unclear. So this leads us to create a new model for understanding rotational motion. And that will be the model of extended objects, and in particular, for our case, rigid bodies. So firstly, what is a rigid body? It is an object that does not change its shape or deform in any way as it moves about, whether it is moving translationally or rotating or some combination of both. We can model a rigid body by extending the point particle model that we already know. We treat the rigid body as a collection of point particles. There are two kinds of rigid bodies that we can consider. We have the discrete case, where we have a bunch of point particles of some mass that are joined together and moving together as one object in some way. Maybe they're connected by light, thin rods that we neglect the mass of. Or maybe they're connected by some force that just keeps them steady. In either case, we have a bunch of point particles in a discrete distribution as follows. So see how I have a bunch of point particles here connected by either some force or some thin rod that we're neglecting the mass of. This whole object moves as one. The other case we have is the continuous case. So that looks like this object that I just drew. This is the sort of object that we usually envision as a rigid body, and it just moves as one object. To model it, we treat each point on it as a point particle. And each point particle on the rigid body has an infinitesimal mass, dm. We can then discuss the mass of the rigid body by talking about its mass density distribution, which in the general case is going to look as follows. It's just infinitesimal mass with respect to volume. Or it might look something like this. So again, with respect to volume, so this is a general three-dimensional case. I don't want to get into the details here, but we keep track of the mass of this rigid body by a mass density, and we treat each point on the rigid body as a point particle of infinitesimal mass, dm. As already noted, the key thing here for this rigid body, whether it's continuous or discrete, is that although there are many particles that compose these objects, the particles move together as one object. Mathematically, what that means is that the distance between the particles of the object do not change as the object moves. So, for example, in the discrete case, I've drawn some green lines between some of these particles, not all of them. I could draw these lines for all the particles. And the key idea is that the distance between particles does not change as the object moves. That is, the length of these green lines that you can draw between the particles does not change as the object moves. The same thing is true for the continuous case. In this case, the distance between any points on the object does not change as the object moves. So these point particles, which are just points on the object, you draw the distance between them, the length of this green line, it does not change as the object moves. That is the mathematical way of talking about a rigid body. Some real-life examples of rigid bodies include such things as rods, or anything that looks like a rod, like a meter stick or a ruler, dumbbells, anything that looks like a disc, such as a pulley, your own pencil or pen or a writing utensil, metal chairs, wooden doors, anything that does not change its shape or deform. This is a rigid body. By contrast, here are some examples of things that aren't rigid bodies. Car tires, for example, as they roll about, they bend and change their shape. They are deforming as they move. Or rubber balls, for example, they hit the ground and they bend and change their shape as they bounce off the ground. We could also have even more extreme examples, like suppose we have a container of gas molecules which are just moving about with random motion. They are not moving together as one object. They are not a rigid body. Or another example, we could have a bunch of point masses connected together, as I showed earlier in the discrete case for a rigid body, but instead being connected by thin rods, they could be connected by springs. And springs, they change their shape. They will change the distance between particles that they are connected to as they bounce back and forth. So that is also not a rigid body. Although I have mentioned examples of rigid bodies in the real world, it is important to note that the rigid body model is an idealized approximation. Real objects will always deform to one extent or another. They just might not deform very much or noticeably for the problem that we are trying to solve. As a result, you could also treat certain things that aren't rigid bodies as a first order approximation. And then if you want more accuracy or precision, then you might include effects from the deformation of the object. So, although car tires, strictly speaking, are not rigid bodies, you can treat them as such as a first approximation to understand the rotation and rolling motion as it moves, because it doesn't really deform that much, or at least not enough that you can't treat it as a rigid body to get some information about it or about the object that it is rolling with. Or another example, the Earth is definitely not a rigid body. It's got an atmosphere composed of gas molecules, and they can definitely change the shape of the Earth, however slightly. But we could treat the Earth as a rigid body rotating about its axis and moving about the sun as a first order approximation. And likewise, we can do the same with other planets and orbiting bodies. So it is an idealized approximation, but you can still make use of it in the real world to get some useful results.